Welcome back to this next video in which we are discussing the auditory system. Okay, so in the previous video we saw the pathway by which the electrical information regarding auditory stimuli is actually going to be transmitted up to the primary auditory cortex, and we saw that information coming from the right ear, the right cochlea, is going to go up to the left-hand side primary auditory cortex. Okay, and I'll just remind you of the pathway that we saw in the previous video because it's very important that we're familiar with this before we move on. So here comes in the first order bipolar neuron central process, and it's going to bifurcate and give off terminal portions to both the dorsal cochlear nucleus and the ventral cochlear nucleus. We're interested at the moment in the dorsal cochlear nucleus. So the terminal portion that goes into the dorsal cochlear nucleus is there going to synapse on a second order neuron which will have its cell body in the dorsal cochlear nucleus. That second order neuron will have an axon which crosses the midline and goes into the contralateral lateral lemniscus, which in this case is the left lateral lemniscus. It will ascend up in the lateral lemniscus to the same sided inferior colliculus, so in this case the left inferior colliculus, and by same sided I mean on the same side as the lateral lemniscus. Obviously this is on the opposite side to the dorsal cochlear nucleus, and in fact everything from now is going to be on the left hand side. So it goes up into the left inferior colliculus, and there it will synapse onto a third order neuron which has its cell body in the inferior colliculus. The third order neuron will then send its axon through the left inferior brachium up to the left medial geniculate nucleus and synapse on a fourth order neuron, which will then give off its axon, which will go in the auditory radiation to the primary auditory cortex, which we've seen is on this gyrus of Heschel, which is a portion of the temporal lobe cortex that faces up into the lateral fissure. Okay, and we've discussed that the primary auditory cortex has this tonotopic arrangement where information about low frequency sounds is going to come to the lateral portion of the primary auditory cortex, and information about high frequency sounds is going to come to the medial portion of the primary auditory cortex. Now remember, we had a tonotopic map on the cochlear duct. Remember, the apical portion of the cochlear duct, that will oscillate most in response to low frequency sounds, and the basal portion of the cochlear duct, that will oscillate most in response to high frequency sounds. So bipolar neurons innervating the apical portion of the cochlear duct, they will eventually transmit their information up to here via the pathway that we've just been talking about. Okay, so their information will arrive up here, and bipolar neurons innervating the basal portion of the cochlear duct, their information through these other intermediate neurons will eventually end up here. Okay, so we saw then the pathway from the right cochlea to the left primary auditory cortex, and that's a really important concept, that it's the contralateral primary auditory cortex that processes information from the cochlea. Now, the exact same pathway is going to exist on the other side. So we're going to have a vestibular cochlear nerve on the left-hand side here, axons coming in here from which are the central processes of bipolar neurons, which are innervating hair cells, will then divide into two, just as before, and we'll come back to the ventral cochlear nucleus, but then with regards to the dorsal cochlear nucleus, the axon will synapse onto a second order neuron, which I'll draw here, which will cross the midline and go into the right lateral lemniscus. It will ascend up to the right inferior colliculus. It'll synapse on a third order neuron in the right inferior colliculus, which will then go up in the right inferior brachium to the right medial geniculate body and synapse on a fourth order neuron, which will then go into the right auditory radiation to the right primary auditory cortex. And again, there's the same tonotopic map with the medial portions processing high frequency information and the lateral portions processing the low tone sounds. Okay, so here comes the big question then. If we have an auditory stimulus, so let's say I bash one of the bars of a xylophone, so an auditory stimulus, is that auditory stimulus going to be processed by both parts of the auditory cortex, so both the left auditory cortex and the right auditory cortex? And from what I've told you at the moment, you would say yes, it's going to be processed by both the right and left auditory cortex, because of course the sound's going to go into both of your ears, and therefore you're going to get signals going up through both of these pathways up to the two auditory cortexes, so right and left. However, that's not what happens, and this is where the picture suddenly becomes a lot more complicated. So let me explain by getting a new piece of paper, and then we'll go forwards. Okay, so what I'm going to firstly discuss is the fact that there is a right auditory field and a left auditory field. So here, this is supposed to represent the plane that a person can exist in, effectively. Okay, and this is known as the azimuthal plane. So you'll often hear people talking about the azimuthal plane when they're discussing the auditory system, and this just means the plane that a person can actually move around in, a plane that auditory stimuli are actually effectively going to exist in. So when we move on the surface of the Earth, effectively we're moving on a two-dimensional surface. That's effectively the azimuthal plane, the plane that someone can exist in. Now, of course, we do live in a three-dimensional world, but approximately we live in a little plane. We're only able to move around two-dimensionally. Okay, so what I'm now going to draw then is someone's head here, and this is going to be the front of someone's head, this is going to be the posterior portion of someone's head, this is going to be the left-hand side, and this is going to be the right-hand side, and we are looking from above. So here, of course, are there two ears. This is the left-hand ear, and here is the right-hand ear. Now, here's the important information. We can divide space up into two halves then, with respect to which ear is closer. So this side is going to be what we will call the right auditory field. So this is the concept of an auditory field. Okay? Space where auditory stimuli can come from. So all of these places over here that I'm now colouring in orange, all of these parts of space are closer to the right-hand ear here than the left-hand ear. So a very important concept is that if an auditory stimulus is present in this right portion of the auditory field, in this right auditory field, then which ear is actually going to hear it A, louder, and B, first? Well, it's going to be the right ear. So these are two important concepts, and these are the concepts of interaural time difference of sounds, so interaural time difference, and also interaural loudness difference. Okay? So if a auditory stimulus is present in the right auditory field, we're going to hear it first in the right-hand ear and then second in the left-hand ear, so there will be an interaural time difference. So interaural just means between ears. Okay, time difference between when you hear the auditory stimulus in the two ears. There will also be an interaural loudness difference, because as sound has to go through more air, so the further you are away from a auditory stimulus, the amplitude of the rarefaction and compression, the amplitude of the pressure difference is going to gradually dissipate. It gets weaker and weaker the further you are away from the sound. That's something that I didn't point out when we were studying the physics of sound, but hopefully is something that's pretty intuitive to you from everyday experience. Okay, so sounds get weaker the further away you are. The amplitude of the pressure difference gradually dissipates with distance. So that means that because the sound has to propagate through more air to get to the left-hand ear, there's also going to be an interaural loudness difference. You're going to hear it louder in the right-hand ear compared to the left-hand ear. So this opposite portion of space over here, which I'm colouring in red, this is what's known as the left auditory field. Okay, so we can divide all of space up into these two portions, the right auditory field and the left auditory field. And here comes the really important concept. This, of course, is not a too difficult concept at all, but now comes the really important concept. Auditory stimuli that are present in the right auditory field. So let's say we've got an auditory stimulus that's coming from here. This is going to be processed by the left primary auditory cortex and not the right primary auditory cortex. In contrast, auditory stimuli that are in the left auditory field, so let's say we've got an auditory stimulus that's over here, this is going to be processed by the right primary auditory cortex and not the left primary auditory cortex. Now, from the pathways that we have discussed so far, that does not make sense, because from what I've told you so far, it should be processed by both the left and right primary auditory cortex, but I'm telling you that each auditory stimulus is going to be in one of the two auditory fields. It's going to be closer to one of the two ears, and it's going to be processed by only one of the auditory cortexes. Okay, and it will be on the auditory cortex that is on the contralateral side to which side of the auditory field the auditory stimulus is in. So I'll repeat this again. So if you've got an auditory stimulus that is in the right auditory field, that's going to be processed by the left primary auditory cortex. Now, what does that mean? That means that it must be the auditory information that is coming from the right-hand ear that is actually making its way up. Because remember, information from the right-hand ear, that, through the pathway that we've discussed, is going to end up going to the left primary auditory cortex. Now, that makes slightly more sense, that we're going to process the information that's coming from the ear that is closer to the auditory stimulus. And it's the same for the left-hand side. If we've got an auditory stimulus in the left auditory field, we're going to process the information that's coming from the left ear and not the right ear, and that means that through the pathway we've discussed, it's going to go up to the right primary auditory cortex because of this crossover. Okay? What we need to see then is how you actually suppress the information coming from the other ear which wants to go up to the opposite auditory cortex, and that's the more complicated part of this pathway, and that's where the ventral cochlear nuclei are going to come in. So I hope now I've given you the motivation for the pathway that we are about to discuss. Okay, so what I'm going to do then is, again, I'm going to discuss this in the context of the right-hand side, but the mirror image is true for the left-hand side. So we're going to imagine that we have an auditory stimulus then present in the right auditory field. Okay, the information is going to be coming into the right ear as well as, of course, the left ear, and we want to see how we're going to suppress the signal coming from the left ear, which is trying to go up to the right auditory cortex, and how we're only going to get the information from the right ear actually going up to the left auditory cortex. Okay, and this is all going to be about interaural time difference and interaural loudness difference. That's how we're going to recognize where the auditory stimulus is. You see, we can work out, because in order to actually achieve this, we need to, at some point in the auditory pathway, work out where the auditory stimulus is, i.e. whether it's in the right or left auditory field. And the way we're going to do that is by looking for an interaural time difference and an interaural loudness difference. We're going to ask, which ear are we hearing this first in, and which ear are we hearing it louder in, and we'll suppress the information coming from the opposite side. Okay, so enough talking about it in theory. Let's actually see how this is done, and it should make it much more concrete. Okay, so we're imagining then that we've got an auditory stimulus in the right auditory field. That means that the information is going to come in first on the right-hand side and second on the left-hand side. And secondly, it's going to be louder on the right-hand side than on the left-hand side. Now, these bipolar neurons, they're all going to also give a process off into the ventral cochlear nucleus, and in the ventral cochlear nucleus, that process is going to synapse with a neuron as well. So I'm going to draw that in now. So here is another neuron that we're activating when the bipolar neuron central process fires an action potential. And it's now going to actually give off its axon, which is going to go into a structure that I haven't drawn on previously, but which is going to be present here. It's going to be present on both sides. Now, these structures are actually the superior olives. Now let's think about where they are actually present. You can see this is a section, remember, of the caudal pons. So these are actually just above the inferior olives, so it makes sense. So these are the superior olives, or you can call them the superior olivary nuclei. So superior olives, if you like, or I'll write their more official name nowadays over here. So the other name that people use for these is the superior olivary nuclei, and I will colour in the superior olivary nuclei in green. So here they are in green. So what's going to happen then is the neurons from the dorsal cochlear nuclei are going to go into the superior olivary nuclei. Okay, and these are going to be excitatory neurons. So when we're getting auditory information coming in here, some of the bipolar neurons that innervate the portion of the cochlear duct that is actually oscillating are going to be exciting these neurons of the dorsal cochlear nuclei, and these are now going to be exciting neurons in that ipsilateral. So ipsilateral means the opposite to contralateral, it means on the same side. So on the ipsilateral superior olivary nuclei. Okay, now it is the activation of the superior olivary nuclei that is going to determine which side, or which is going to encode, I should say, rather than determine, is going to encode which side of the auditory field the auditory stimulus is present in. So on the other side, on the left-hand side here, you're also going to be getting activation of the superior olive here by the bipolar neurons that are activated on this side. But for a start, the activation is going to occur later on, and secondly, it's going to be to a lesser extent because of the interaural loudness difference. Okay, now, the more activated superior olive and the superior olive that was activated first is going to make sure that the contralateral superior olive is inhibited, so that it's a case that one is turned on and one is turned off, and this is how you're going to actually encode the information of which side of the body the auditory stimulus is present. On the side where the auditory stimulus is present, the superior olive will be turned on, and on the side where it's not present, the superior olive will be turned off. And this is how it's going to work. So this superior olive that was activated first because the auditory stimulus was on this side and therefore arrived here first, it's going to send some neurons' axons across into a nucleus on the side of the contralateral superior olive. So we now need to draw in two other nuclei here. Okay, and let me just move this and make sure it's straight. Okay, so these nuclei, where should I put their name? These nuclei are known as the nuclei of the trapezoid body. So first I need to tell you what the trapezoid body is. Okay, so the trapezoid body is made up of a lot of axons that connect the two superior olives together. So we can see that this superior olive here, I've so far described that some neurons which have their cell body in the superior olive are going to go across and try and do something to the other superior olive. So there is connections between the two superior olives, and this portion of the caudal pons where you've got lots of fibres crossing between the two superior olives is known as the trapezoid body. Okay, and in the trapezoid body there are two nuclei known as the nuclei of the trapezoid body. So nuclei of the trapezoid body, and it really is now just becoming, I'm writing wherever I can find space. Right, and I think what I'm actually going to do is go over onto another piece of paper and draw this out a little bit bigger. We'll come back to this picture because I want all of this diagram that I've got here, but I also want it to be more clear than it's going to be on this picture. So what I'm going to do again is I'm going to now draw out the superior olives with a little bit more space here. So here are the two superior olives. We've still got the right hand side and the left hand side here, and now we've got these nuclei of the trapezoid body present here. So all I've done is copied this little bit of the caudal pons section out onto here. Okay, and I'm going to write out the name of the nucleus of the trapezoid body again. So nucleus of the trapezoid body. Okay, so of course you have two nuclei of the trapezoid body. You have a left nucleus of the trapezoid body and a right nucleus of the trapezoid body. Now, we've discussed that on the side where the auditory stimulus is present, you're going to be getting the activation of the ipsilateral superior olive here and it's going to be occurring first. And what this superior olive is now going to do is it's going to try and inhibit the other one, because we want this to be an on-off situation. We want this one to be on, which will show us that the auditory stimulus is on this side, and we want this one to be off, which will show us that it's not on that side. So what's going to happen is some of the neurons inside the superior olive, they're going to send their axons over into the nucleus of the trapezoid body on the contralateral side, and in the nucleus of the trapezoid body there are inhibitory neurons, okay, which will send their axons into the nucleus of the this superior olivary nucleus on the same side as it. Okay, so this neuron here, which I'm colouring in red, this is an excitatory neuron, okay, and it's going to be activating the neurons in this nucleus of the trapezoid body, which are inhibitory neurons, and which will go into the superior olive over here and inhibit it. So this is the way that you prevent the contralateral superior olive becoming activated. This superior olive got activated first because of the interaural time difference, and it's now going to make sure that this one is inhibited already so that it can't become activated. So now when the auditory information arrives from the other ear, from the left ear, of course it will come in later, now you're getting stimulation from the dorsal cochlear nucleus on the left hand side here, but it's no use because this one is inhibiting very strongly now. The nucleus of the trapezoid body on the left hand side is activated to inhibit the superior olive on the left hand side, and that stops this from becoming active. Okay, so that's the way in which the right superior olive is going to become activated if the auditory stimulus is on the right auditory field, and the left superior olive is going to be inactivated if the auditory stimulus is on the right auditory field. Now let's go over the opposite situation. So if it's the opposite situation, if the auditory stimulus is in the left auditory field, then of course the information will arrive on the left hand side first. Okay, so the left superior olive here will become activated first. It will now send axons from some of its neurons into the nucleus of the trapezoid body on the right hand side here, and the same thing will occur in the nucleus of the trapezoid body on the right hand side. You'll have inhibitory neurons, so I'll colour the inhibitory neuron here in blue, and I'll colour this neuron here from the superior olive in red. So this superior olive has become activated first. It now goes over and activates the nucleus of the trapezoid body on the right hand side, and that contains inhibitory neurons which will go into the superior olive on the right hand side and inhibit it. So when the dorsal cochlear nucleus tries to activate this right superior olive later because of the interaural time difference, it won't be activated. So that one will be turned off and this one will be turned on. So I hope that now makes sense what the superior olives are doing. They are working out which side of the auditory field the auditory stimulus is actually present on, and they're doing it through the interaural time difference and also to a lesser extent the interaural loudness difference. You have to factor in that as well, that the initial stimulation to this one will be greater than the stimulation to this one. That will also help to make sure that this one's the one that will be turned on and this is the one that will be turned off. So both of these factors are going to be pro this one being turned on and this one being turned off if the auditory stimulus is in the right auditory field, and will be pro this one being turned on and this one being turned off if the auditory stimulus is in the left auditory field. Okay, so the superior olives are going to decide which auditory field the auditory stimulus is actually in, or which side of the auditory field the auditory stimulus is actually in. So going back to the story where the auditory stimulus was in the right side of the auditory field, then we'll get activation of the right superior olive. What is going to happen now? Well, there are neurons in the right superior olive which send their axons across, so the axons are going to cross the midline in the trapezoid body. So the trapezoid body is all of these fibres that appear to run between the two superior olives. This fibre isn't actually going to go to the other superior olive, but it's still going to move with all those other fibres in the middle there that is counted as the trapezoid body. So it goes round like so, and then it's actually going to go into the contralateral, lateral, then meniscus. So some of the fibres of the superior olive will cross the midline in the trapezoid body, they'll go round the contralateral superior olive here, and then they'll go into the lateral lemniscus on the contralateral side, and then they'll ascend up, of course, to the inferior colliculus. And what's this going to tell this inferior colliculus? Well, of course, it's going to tell it, you're the right one. Because remember, this is the left inferior colliculus, and this is carrying the information up to the left primary auditory cortex, which is the one that's supposed to process the information from an auditory stimulus coming from the right side of the auditory field. So it's going to go up and say, go ahead, pass the information on, but also, could you tell the other inferior colliculus to block any information coming through it? Because we do not want the information from the left ear going up to the right auditory cortex, because that's not supposed to happen. We only want information from the right auditory field processed by the left primary auditory cortex and not the right primary auditory cortex. So it comes up into this contralateral inferior colliculus. It says, okay, you can conduct your information absolutely fine, but could you tell this inferior colliculus not to? So what actually happens is some neurons in the inferior colliculus, so other neurons in the inferior colliculus, are going to have these neurons from the superior olive synapsing onto them, and they're going to cross the midline in something known as the collicular commissure. Okay, so there is a connection between the two inferior colliculi known as the collicular commissure, and this is where some neurons that have their cell body in the inferior colliculus can actually cross the midline and inhibit the neurons of the contralateral inferior colliculus, and it's going to inhibit these third order neurons of the contralateral inferior colliculus. Okay, so remember we discussed this pathway, the pathway that we discussed in the previous video involved the second order neurons from the dorsal cochlear nucleus going up and synapsing on these third order neurons in the inferior colliculus, in the contralateral inferior colliculus. These are the neurons that we're now going to inhibit. Okay, so there are these two populations of neurons then in the inferior colliculi. The neurons that are the third order neurons as part of the pathway that we saw in the previous video, and then these neurons that are being synapsed onto by neurons from the superior olive, and which are going to cross the midline in this collicular commissure here and inhibit the third order neurons on the opposite side. Okay, so this is the collicular commissure, and I'm sorry the picture isn't a little bit more clear. I'm trying to think what I could do to draw this out again. I'll try and show it a little bit more clearly on here. So, some of the neurons of the superior olive here on the right hand side will cross the midline like so. Okay, they will go up into the contralateral lateral lemniscus here. Okay, so this is the lateral lemniscus here. So they'll ascend up there, and then they will go to the ipsilateral inferior colliculus, which I'll draw here. So we'll have the two inferior colliculi shown here. So here it comes to the ipsilateral inferior colliculus, and there it will activate neurons that are going to cross the midline into the contralateral inferior colliculus and inhibit the third order neurons that are being synapsed onto by second order neurons from in this case, right lateral lemniscus, and block that transmission of information between the second and third order neurons. Okay? Right. So that is the way in which the information is not going to be allowed to be transmitted up from the left-hand ear up to the right auditory cortex by blocking this transmission from the second order neurons up to the third order neurons on that right-hand side. Okay, so I'm going to summarize all of that again because it's very, very complicated. So, we'll do it again for the right hand side. In fact, actually no, we'll swap over this time. We'll do it for the left hand side to make sure that that side's clear as well. So let's say that we have an auditory stimulus that is in the left auditory field. What's going to happen is we will get information coming up both vestibulocochlear nerves, because both of the cochlea on both sides will be activated by that auditory information. The key thing is that on the left hand side it will be louder and it will be sooner than on the right hand side, so it will come in first and it will come in louder than on the right hand side over here. Okay, now on the left hand side we are going to go through this pathway to transmit the information up to the right auditory cortex. I'll remind you of that pathway. Here come in the bipolar neuron central processes. They will bifurcate and give one process to each of the two cochlear nuclei. The dorsal cochlear nucleus is going to be the one that's actually going to transmit the information upwards. Okay, so you'll synapse onto second order neurons in the dorsal cochlear nucleus. They'll cross the midline into the right lateral lemniscus here. They'll go up to the right inferior colliculus, where they'll then synapse on third order neurons in the right inferior colliculus. Okay, then what will happen is the third order neuron will send its axon into the right inferior brachium, and it will go into the right geniculate body to synapse on the fourth order neuron. The fourth order neuron will then send its axon into the auditory radiation on the right hand side and will go to the right auditory cortex. How are we going to block the same thing happening on the left hand side? Well, what's going to happen is we're going to also be activating neurons in the ventral cochlear nucleus here, which are then going to be sending their axons into the superior olivary nucleus on the left hand side here. Okay, and they're going to be exciting this left superior olive here. The left superior olive has been activated first and more strongly than the right superior olive here, and that means that it's going to win this fight. It's going to be activating the right nucleus of the trapezoid body to inhibit the right superior olive, and it's going to win, even though the right superior olive will be activating the left nucleus of the trapezoid body to inhibit the left superior olive. Of course, its activation of that nucleus of the trapezoid body will be weaker than the left superior olive's activation of the right nucleus of the trapezoid body. And I know this is extremely complicated, but overall this one will win and this one will lose. This one will be activated, this one will not, and that's because of the interaural time difference and also because of the interaural loudness difference. So the left superior olive will be turned on, the right superior olive will not. The left superior olive will then send fibers up in the contralateral lateral lemniscus. They'll cross in the trapezoid body here, and then they'll go into the right lateral lemniscus. They will ascend up into the right inferior colliculus, and there they will synapse onto neurons that are different from the third order neurons that are up in that inferior colliculus. There are other neurons up in that inferior colliculus which will then cross the midline on into the left inferior colliculus along the collicular commissure, and will inhibit the third order neurons in the left inferior colliculus here. Okay, and by doing that, they will stop the transmission of information from the second order neurons that are transmitting information from the right ear to the third order neurons that will be taking the information onwards towards the left primary auditory cortex. Okay, so there is the summary of this. That is how auditory information is only going to be processed by the primary auditory cortex that is contralateral to the side of the auditory field where the auditory stimulus is present. Okay, so that completes the central auditory pathways. We will have a break there. This is a complicated pathway. Take time to take it in. And in the next video we'll just say a few words about hearing loss.